Okay, well, yeah, thanks for having me all the way from Huntsville, Alabama, and I will be kind of lecturing today on two subject areas. One is pretty much the first hour and a half today is going to be on the 0 to 1 hour convective initiation work and kind of where I started with it, how the algorithm developed, where we are today is where I'm going to finish off with, and then some of the challenges that we encounter along the way, as well as kind of how we're going to look forward to improving the methodology. And as this talk's all going to be about nowcasting, in other words, what goes on in the next 1 to 2 hours, the next talk after this is going to be on what do you do when you have a mature convective storm, and how do you use satellite observations to say something about what's going on, either from a turbulence perspective or a severe weather perspective. So anyways, I'll start off by asking a question. Why do we nowcast? Let me start that over. The methods for forecasting the weather in the 0 to 6 hour time frame are generally different from how we forecast weather from 6 to, say, 24 hours. How are they different? Why is nowcasting unique from, say, other forms of forecasting? Does anybody have a guess on that? See, a lot of what I do is actually going to be what I will term nowcasting. So it's figuring out what's going to happen right now for the next 1 to 2 hours. Those methods of forecasting contrast to numerical weather prediction. So why can't we use numerical weather prediction in this, say, 0 to 2 or 0 to 3 hour time frame? Yeah, this is a really key part of understanding meteorology. Why don't weather models work very well in the first 3 to 4 hours? Well, if you haven't had a numerical weather prediction class, the big reason is they have a spin-up time. So if you initialize a model, and I actually do a lot of data assimilation research, so trying to improve the initial condition of the forecast or the initial condition, so you actually apply the equations of motions and all the Navier-Stokes equations on this initial condition to create a forecast. Well, as it happens, because models are of finite resolution and they can't be at resolutions of, say, 50 meters right now because we don't have the computer power, the models take roughly 4 to 6 or 8 hours to spin up and build in all the fine scale detail. So when we're talking about which cloud's going to make rain or which cloud's going to make lightning or where's that volcanic ash plume going to go in the next 1 hour, what do you think's the best way to make that forecast? If a model doesn't work, what's the other best way to make a forecast? If your best friend called you up and said, what's the weather going to be like in 10 minutes, what would you tell him? Probably you'd look outside and say, okay, well, I don't see many clouds in the sky. It's been sunny for the last 4 days. I'll bet you it's still going to be sunny. What you're doing is you're linearly extrapolating into the future. You're taking the current trends and you're extrapolating them forward. Well, that's really what we're doing with satellite observations to make these convective initiation, or where is it going to rain in the next 1 hour. So we know where the cumulus clouds are, and we can use satellite observations like this. This is actually over Cuba. And we can pretty much identify which clouds are already making rain, which clouds probably are growing, which clouds are cumulus clouds, and which ones are cirrus. So we can do a really good job of that. And the talk this morning did a good job describing some of the other pieces of information we can pull from satellite observations. It's not just where it's sunny and where it's clear. We could pull out microphysical information from these as well. So a big part of the talk, what I'm going to go through now in the next hour and a half, is describing methods of nowcasting using linear extrapolation, starting off with some very simple approaches, but then getting into more complex approaches as we include more observations. And when I say more complex approaches, that's really going to be more statistical approaches rather than saying, just linear trends. And if we know the trend now, then we can diagnose the trend later. So anyways, that's kind of an important lesson for forecasting. And I would encourage everybody in this class to take a numerical weather prediction class at some point in their meteorological career, because it teaches you an awful lot of why we can't make a good forecast. So anyways, this is where my research in this started, and it started back in about 2001 after I got my Ph.D., and this is in a completely different area than I got my degree in. And mostly it started out of frustration. I was looking at the weather before this class started because a big reason or a big part of what occurs in North America, as well as here, of course, is we have scattered thunderstorms that will have almost could develop any time on any afternoon in the summer for 3 to 4 months in a row. And if you live in Florida where it's very humid, this is half the year. So, and the whole point is that oftentimes we're given this forecast of partly cloudy with a 40% chance of rain or a 30% chance of rain. And as a user of weather data, this is really very useless. I would often, when I worked for the Weather Service, I would get a phone call or two every few days from a guy laying cement or a guy doing something outside saying, is it going to rain or is it not? And I got one guy, he said, well, he got mad at me and he said, you're the weather forecaster and you can't tell me what's going to happen. So, I cried for 6 months and then went and got my Ph.D. So, but anyways, realistically, we're really unable to make this forecast of where deep convective storms are going to occur. And as you know, if it was partly cloudy with a chance of rain today, you're either sunny and you can do something, or it's lightning and really raining hard, which is a completely different, it's like two completely different sides of things. So before I start to talk, I think it's actually important to define things. That's one of the first things you should do if you're doing a master's thesis or PhD is set your definitions. So convective initiation here is defined as the first occurrence of a greater than or equal to 35 dBz rainfall echo at the ground or at the minus 10 degrees C altitude. This is a heavy rain shower. It's not to say that I'm not forecasting or nowcasting for light rain or drizzle, but for the most part, this lecture is going to be focused on convective storms. And these definitions date back to like the mid-1960s, and they're used pretty heavily in some systems. Even the RDT or the CB-TRAM most likely still use these definitions. So anyways, for the remainder of the 5,998 slides I have left to go here, that's obviously true, and that's not a joke. So what can satellite observations measure within growing convective clouds? And over the last few days, we've actually seen some of this, but I think the important question is what they really cannot do as well. So we have to understand the limits of the data. I'm going to go through an overview of the nowcasting system, that kind of the thought approach that I took to when developing this. The methodology that I've been developing over the last 8 to 10 years, how we're expanding this to forecast which cumulus clouds are going to eventually make lightning and how can we do this, saying something about which convective clouds are going to be strong storms versus which are not, and then new techniques and directions, as I said before. So anyways, we can start pretty much with where information comes, kind of what are the factors for convective storm initiation. I think most people are fairly aware of this. You're not going to get a convective storm in the middle of January unless you're over a warm water body in the northern hemisphere, because there just isn't any instability. So we can pretty much use model data, even though I said models don't do a good job forecasting where each individual storm do. They actually do a good job forecasting the basic background environment. So if there were scattered storms around Germany this afternoon, we pretty much would know what the instability is, what the capping inversion is, how much moisture is down at low levels. We can actually use the satellite observations then to diagnose things like cloud top temperature, the growth rate, the glaciation, whether the top of the storm is turning to ice or not. We can actually, if we know things like the freezing level, you can say, is this going to be a warm rain process storm or is there going to be ice microphysics involved? And that's something where towards the end of my talk, I actually will say something about this, because this has a lot to do with how the internal aspects of the storm are going to evolve and whether it's going to make lightning. You're really not going to get a lot of lightning if you have a lot of water in a cloud and very little ice. We have interactions with the ambient environment, other clouds. We have outflow boundaries, things that we can actually see in satellite. So you have colliding outflow boundaries. And then if you look at things like lightning presently, and we've seen some of this, we can say, You can define the type of lightning, the amount, the polarity, the altitude in the cloud with respect to anvil, what have you. So there's a lot of information in our observational data sets right now that we can draw into this problem of nowcasting. And I do want to preface my talk that there's a lot of people who've actually worked on this problem in addition to the work I've done with satellite. There's systems like the Auto Nowcaster and the rapidly developing Thunderstorm and CB-TRAM that integrate awful lots of pieces of information on that 0 to 6 hour time frame to try to diagnose where storms are now, where they're going to develop, where they're going to move, where they're going to decay. I've been focused on the initiation problem. So this leads me to kind of this question is what can and what we cannot determine from satellite observations about convective clouds. And if you go to the momentum equation, and now this is actually in kind of a notation where U would be all three vectors, U, V, and W, and K would be these two terms. Actually, there should be K's after them. They're just applying the vertical direction. But anyways, so you have this perturbation pressure. Realistically, this would be a lovely quantity if satellites could diagnose it. I don't think it's really possible without a lot of other information. So we really can't say much about pressure gradients in the atmosphere from satellites, and that's really too bad. From the winds, we actually have quite a bit of momentum information. Where do you think cloud momentum or winds come from if you use satellite observations? How would you get, can anybody give me a quick answer on, do you know of a product that, or how you get winds, how you get wind information from satellites? Yeah, cloud motion winds. These have been around since the late 1960s, early 70s, when you had the advent of the first geostationary satellite where you take two frames and you take the difference. As long as you can identify one cloud in one image and one cloud in another, you can actually get winds. So this is actually very helpful to the nowcasting problem because we can actually say something about where the clouds are moving and how, if you know where they're moving, you can say something about how an individual cloud is evolving. You can get things like feature expansions, how quickly a cloud is growing in time, how the anvil is growing. Now when you get to something like the buoyancy, which dictates whether a cloud is actually going to grow, this is a little bit more tricky. Partial thermodynamics, we'll see on the next slide. Satellites can retrieve to some extent moisture and temperature profiles. And like I said, I'll say something in a minute. In cloud water and ice contents, I mean, when you get things like updraft water loading and what have you, this becomes a little bit questionable. If you understand the moisture profile from satellites, you probably can say how much water and ice are going to be affecting a growing cloud, but there's caveats to that because satellites don't see inside of clouds. And then basically, again, this is a function of temperature and moisture retrievals. And if we look at the thermodynamic energy equation, which is another more basic principle, focus on the second term here, which basically represents the effects of diabatic heat sources in sinks or latent heat release. So to some extent, some of the TRMM products, the microwave generated tropical rainfall measuring mission products, have been used to diagnose things like latent heating, and that's based on precipitation. So if you have X amount of precipitation, you're going to get X amount of latent heating. So anyways, to some extent, I would say satellites can do a little bit on this level to diagnose things in terms of what it comes down to. So retrieved quantities, as we saw this morning, microphysical cloud properties such as optical depth, ice water path, emittance, reflectance, etc., can be fairly well retrieved from satellite, especially if you have a background information from a numerical weather prediction model. Aerosols can be pretty well retrieved from models. They actually go into affecting the internal microphysics of clouds, which is the precipitation generation process. And so profiles of temperature and moisture, and these again go for stability estimation, but also affect terms like this, as well as affecting things like the water loading in the buoyancy calculation. But I will say this, is that, does anybody know what the biggest limitation for temperature and moisture retrievals are from satellite? So when you actually do a retrieval of temperature and moisture, you pretty much have to say, okay, if you have X amount of channels in the infrared, each channel represents radiation emitted from a certain layer or a layer, basically represented by a weighting function. Right now, the best instruments we can use for temperature and moisture retrievals are so-called hyperspectral instruments that may have thousands or 2,000, 3,000, 4,000 channels. Presently, they'll do a fairly good job at capturing the general or the gross temperature and moisture structure, but they are limited. For one, the retrieval process when you use thousands of channels is extremely numerically intensive. And two, things like temperature inversions, which are very, very critical to determine if a capping inversion is whether a cloud is going to reach the level of free convection, require details on the order of 50 meters or 10 meters. And presently, and I'm not trying to be negative, but I'm saying from what I've seen, we can't quite capture that level of vertical detail. Radio sounds offer a very, very good look at the moisture and temperature profile, whereas satellites give a little bit more washed out view. But anyways, I go back to these basic principles because it is really important for us when we're doing nowcasting to probe the satellite observations for what they can offer and kind of try to avoid not overselling the observations for in cases where we pretty much know they're not. So in other words, if I wanted to derive a momentum budget for a convective storm, that perturbation pressure term is going to be really elusive. I can't necessarily fill that. But anyways, that's an aside. But for convective storm development using satellite alone, it actually there's a lot of information here, and so that's pretty much what I did. So kind of the thought process I went through, this particular event, even though it was in 1990 when I was 21 years old, anyway, I have a sense of humor, so occasionally I try to inject that in here, but sorry for failing. But anyways, no, this was this particular convective storm developed on a day when it was extremely humid, and I was actually living right in a town about right here, Madison, Wisconsin. This storm went on to produce a huge tornado in the Chicago area. And my question from this is, how in the world could we have possibly guessed that this cloud here was going to go on to produce a storm here? And the same thing for being said here. You have this relatively innocuous cloud here, and it produced the storm here. We have this whole line of cumulus clouds, and I think the experienced forecaster can in fact say, well, these little lumpy dots are probably cumulus clouds. Yet this is the only storm that actually went on to make a tornado. All these other ones really didn't do very much. So I spent a fair amount of time trying to figure out, what goes into making a forecast like this, or if you had to make a forecast that looked like this. I actually made this up as kind of a prototype for a system that I would like to develop. How would you go about doing this? And at the time, there were people at the National Center for Atmospheric Research who were working on the Auto Nowcaster. They had some of these ideas, and their biggest limitation at the time was that they really didn't know how to use satellite observations very well. They used them, but they didn't understand what value they all had. And so then I was kind of challenging myself to say, again, what aspects of a growing cumulus cloud can you actually diagnose using satellite? So anyways, a system that, again, this is kind of interesting. I pulled this slide out when I was developing this talk, something I put together in probably 2001. And it turned out to be very, very similar to what I have today in terms of some of the information that you'd want to bring into a nowcasting system that would be heavily satellite-centric. Hourly weather data, well, effectively, I never really did that. But model forecasts and analysis, we use that all the time. Satellite-derived weather inputs, this is winds. For the most part, it's satellite-derived winds for tracking. Real-time remote sensing systems, you pretty much could bring this into a system to diagnose instability. Cloud identification software, this is really key, and I'm going to show just one slide on this, or a couple slides on this in a little bit, but this is really key to identify which clouds are cumulus, which clouds are altocumulus, which are cirrus. Kind of applying a scoring or a learning algorithm here. So you take all this information with some rules, and you would basically then be able to produce storm initiation predictions and convective type. We really are just getting into this work now. This work is actually something we produce routinely. So the one thing I did when you look at satellite observations, is that they really offer this low latency. So in a good environment, you can get a new scan from MSG or GOES in a matter of 1 to 2 minutes. Presently, they're 15 minutes separated in time in the United States, but in Europe, you can get 5-minute imagery, which is really, really nice. The trend is towards even 1-minute imagery from GOES-R or 2.5-minute imagery from MSG. So that's actually really, really good in the nowcasting world. The resolution, less than 1 kilometer in the visible. Now, if you go to other satellites like MODIS or VIRS, we get snapshots of, we get imagery that's less than 1 kilometer in resolution. But what is the biggest limitation for doing nowcasting with a polar orbiter satellite? How often do we get a MODIS or a VIRS overpass or MEDOP overpass in Europe? Like a couple times a day, okay? So if you have a cumulus cloud here and 4 hours from now when you get another overpass, where do you think that cumulus cloud is going to be? Who knows? It's going to be long gone. So you really need this very frequent update that comes from geostationary. 3 to 4 kilometer resolution in the infrared. We're going to probably be down to 2 kilometers with GOES-R. The sounder, MTG is going to have a nice sounder, hyperspectral. Right now, 10 kilometers with GOES. This allows you to derive products like soundings of moisture and temperature. And hyperspectral is really going to be the way to go in time. So, and we can do satellite-derived products, as I mentioned, temperature and moisture for stability, winds, cloud microphysical properties. We're getting into that now. You can actually bring in these advanced remote sensing systems like VIRS and MEDOP just to give a truth for the situation. So if you can take a very high resolution snapshot of a cloud, that's actually really, really good. Numerical model prediction fields, this is not satellite observations, but it provides important background information. Weather radar, including dual polar metric fields. This is a validating data set more than anything right now. We're getting into relationships between satellite and radar. But just validating how well a convective initiation algorithm is doing, you need weather radar. And then lightning observations, which help you figure out which storms are thunderstorms and which are not. And what I wanted to mention before, the best thing for a satellite only or a satellite-based convective storm initiation algorithm is that it provides background. It fits very nicely into systems like the Auto Nowcaster or the CB-TRAM or RDT or Coalition that monitor not only storm initiation but evolution. So I think the niche for some of this nowcasting work is not a standalone system, but it's something that can fit into other systems. So when you look at the processing methodology, now this is a kind of a ubiquitous statement for any type of research you do. It doesn't have to be doesn't have to be satellite work, is you really have to understand the scales of your phenomenon you're studying. So in terms of convective storms, does anybody know what the cumulus cloud scale is by definition? Can anybody take a guess?
The cloud height, you mean? The cloud height.
Well, the scale.
The height.
Well, I'm talking about, yeah, the height, the width, the time. So the height, you said.
12 kilometers.
Well, yeah, say the height?
Let's say 12 kilometers.
Right. So 2 to 3 kilometers by 12 kilometers. Does anybody have a sense for how long your average cumulus cloud lasts?
2 hours. 2 hours.
Even a small cumulus cloud? Maybe 20 minutes or a half hour. Yeah, a large thunderstorm, that's right, 2 to 3 hours. So whether you're studying, so now if you're studying something like a synoptic scale wave, obviously then you have a whole different issue of scale. So I kind of looked at this from a scientific standpoint. Anyways, so we have these if you look at the meso alpha to meso beta scale, so roughly 20 to 2,000 kilometers, 20 is a really low end. We can do things like per cloud or per pixel processing that actually gives us information at that level. We can do convective cloud typing, identification of cloud types, which has actually been done for quite some time. We can actually do pattern recognition. So if you take groups of pixels, you can do things like, you probably could develop a pattern recognition scheme for a sea breeze front or a anvil or of a flanking line on a thunderstorm. We can do things like convective cloud history and evolution if the feature is big enough. If it's really, really small, if it's less than a pixel, we really can't. In fact, the talk this morning, there was a really good slide in there that shows when you represent a cloud scene with 1 pixel, you're basically taking an average. So one of the biggest problems we have with cumulus clouds is that our pixels are 3 kilometers in the IR, maybe 4 kilometers or more, and the cumulus cloud is what you said, 2 to 3 kilometers. Well, you get kind of a mixture of the ground and you get the cloud. Well, that's really not very physical. It's just something. So that's kind of the best we have. That's why higher resolution is better. And then I said something about cloud motions. And so when you take an image like this, the human being can pretty much stand here and say, well, I know this is cumulus clouds. Here's some active thunderstorms. This might be an area of active, we want to pay attention to this. But realistically, there's a lot of these other areas where we know they're clear. So this is some of the initial analysis we'd want to do on this scale. If we look at synoptic scale, we can do things like kind of regional cloud typing or identification, which gets into air masses. We can assess the convection itself, so active convective regions, non-precipitating convection, regions supportive of convective development and growth. This has to do with just general instability. And then potential hazards. So in the United States, we have the Storm Prediction Center, which analyzes where there's likely to be severe storms developing. So this is kind of information we could bring into this process. This convective cloud mass, this is something where this actually should have been a little bit ahead. But this is actually a really, really robust system where if you use MSG and you use all channels, you can pretty much go and this is just a few cloud types that come out of here. So you can say obviously which clouds are ice, which are convective cumulus clouds, which are towering cumulus, so we can make these fine scale definitions, which are warm clouds, but they're not glaciated, so that would be a stratus or a thin water cloud, etc. So we can actually do some of this really nice processing using satellite observations. In fact, without this product, a lot of what I do wouldn't work very well because we need to know which clouds are cumulus. This is some of the synoptic scale analysis. This is a really old figure, but for the most part it does demonstrate if you just use sounder observations, you can diagnose where the highest moisture is in the atmosphere. This is a lifted index product, so we can diagnose where the instability is. This gives some general background information on instability. And so if you look at this from a perspective of what can we take to bring into this product to make a convective initiation nowcast, we can use single pixel processing. So just figuring out on every 3 by 3 kilometer region for MSG, which clouds are, say, glaciating or which clouds are growing very rapidly. Multi-pixel processing, we can do objects and track objects over time, and that's something we're really doing well now. Single pixel processing of multi-pixel scale features. So we can do microphysical properties of clouds within lines or clusters, and this is something that we can generally bring in. This is an important concept in the sense that clouds here that are behaving, say, over this location, if you go 20 kilometers away or 50 kilometers away, chances are likely the environment's going to be similar enough that what's going on here could be applied to nearby storms that have not yet formed. So this is something we're doing. And again, general cloud top warming or cooling. So are the clouds generally getting more intense with time or taller with time in a region or not? And so this is another example of some single pixel analysis that I've done pretty much, and we're going to see this a lot when we get to the next talk, is things like overshooting tops and where the storms are already intense. And a product like this becomes really, really valuable when you wouldn't want to produce a convective initiation forecast where it's already raining or where it's cloudy. So when you look at this, and here's an example of some multi-pixel scale work that we could get into. There's no reason at all why you couldn't diagnose lines of cumulus clouds, which help determine where a capping inversion is breaking. Clusters of cumulus clouds over the ocean. These are other cloud lines over the ocean, and these actually are background information that we could bring into a nowcasting system. And so this is another kind of an example of single pixel processing of multi-pixel features. As far as what we've done so far, we really have not gotten to this point, but in effect, we are starting to get to this point where we're using clouds of different type, like cirrus clouds, to help solve some challenging problems in the nowcasting world. And this is another example of sounder information. These are our cloud motion winds. This is actually a very key component to what we've done with the satellite processing for convective storms, simply because if we can, man, I hope my voice doesn't go now. If we can diagnose which clouds are cumulus, then we can actually track them as they grow. And so this is a really important quantity as well. So the convective initiation methodology, right now we bring in satellite observations, ancillary information from models, and then I'll just talk about the processing and technique development. So, so basically what I did is I started off with, how would you actually, what I kind of went over here before, how would you actually solve this problem in terms of, what pieces of information you would. Well, then the next thing I did was a literature search and try to figure out, well, if I have for GOES, because this is all what I was working with, not MSG, how would you actually bring in, we had four infrared channels. So we had 3.9, 6.5 or 6.7, 10.7, and 12 micron or 13.3. And so a lot of previous work from other studies had used channels to figure out different attributes of clouds. So this would be the height of the cloud, the growth rate of a cloud using the trends of, say, the cloud top temperature. Things like the height of the cloud relative to the middle or upper troposphere, and whether the cloud's top is glaciating. And this is actually key information. But what I'm learning with MSG, or what I've learned, is that the addition of 9 infrared channels really gives us a lot of information, better information on things like cloud top glaciation. So it's kind of what I mentioned at the beginning. Man, I hope my voice doesn't go now, because I got a whole 2 hours left. So I think I'm going to talk a little quieter for a little bit. But one of the methods that we initially produced in making a nowcast is if we knew which cumulus clouds were, which pixels contained cumulus clouds, and we could apply each one of these tests on a given pixel, we had what was called a simple scoring approach. So this was pretty much saying that if we define these critical values for a given pixel, we would say that if a cloud passed 6 of 8 critical tests, so in other words, if the cloud's top temperature was less than 0 Celsius, which meant it was cold, if the cooling rate was -4 or less, that means a strong updraft in the cloud. If we had the 6.5 - 10.7 channel difference was between -10 and -35, that's a good sign that the cloud is deep. If we took the time trend of this field, it would or 13.3 - 10.7 or 12 - 10.7, we could apply this. Again, that's another test for, is the cloud tall? So we're looking for a cumulus cloud that's got an updraft in it, that's growing, that's tall. If we apply the 6.7 - 10.7, this is another test for whether the cloud is actually tall. Then what we could do is we can actually take time trends of these channel differences. These actually give us a sense for, is the cloud growing not only down low, but is it growing up high? So a simple scoring approach would say if 6 of 6 of these tests passed for a given cloud, that's a really, really good sign that the cumulus cloud is continually going to grow and make rain. And I have a couple schematics coming up that describe how these individual channel tests work. But some of the newest things we're doing, which is actually very interesting to me, is if you bring in other information and you develop something that's called a training database. So in other words, You take tens of thousands or many thousands of cases and you evaluate what these individual scores are per cloud with some truth radar, then you can actually develop statistical approaches that provide a probability. And then from that point, you could actually bring in other information like the stability in the environment to say something about, well, you know, this cumulus cloud is growing really, really fast, but guess what? It's generally very stable. So we would downweight that. But anyways, so this is some of the kind of where we're headed. This is how we develop the training database. To give you a sense for anybody who's doing research, kind of one of the most frustrating aspects of doing research is not only developing a method, but proving how good your method really is. We have spent a lot of time, on the order of 5 years, coming away with a method by which you could prove to yourself, using real-time radar observations or historical radar observations, if you identify clouds that are cumulus and you create objects and you apply these tests, which ones make rain and which ones don't, and why don't the ones that don't make rain, what's the reason behind that? So this is actually something where we produced a database of close to 10,000 events that gave us a sense for the hits, the misses, the false alarms, and our general skill of our procedure. So from GOES, with only 4 infrared channels, I was able to this is actually, at one time I had 8 tests, okay, different things that show different attributes of clouds. A study I did in 2010 with the help of EMET said, you can use up to 6 tests that give you a sense for how deep the cloud is. You could use up to about 7 tests of using different channels to talk about cloud top glaciation, which is really important when it comes to lightning and making rain. You can apply another 8 tests to figure out how strong the updraft is. Now, obviously, this is overkill, but it gives a really good sense for how different amounts of spectral information in the infrared can be applied to clouds. Cumulus clouds to just test and verify whether they're going to make rain. This is the same idea, but using just visible information. So if you use the 3.9 visible reflectance, 1.6 visible reflectance, this Ph.D. field is actually a kind of a lumpiness field, or it's a variability field in the high resolution visible. You could use the 0.6 channel or the 0.8 channel in here as well, just to give a sense for which clouds look more lumpy from satellite. And this is actually, if you use some of these RGB composites, this is really a lot of what goes in here. So from MSG, even though it's got 9 channels, we get a wealth of information. Well, 12 if you include the visible, high resolution visible. We get a wealth of information on some of these physical attributes of growing convective clouds. So this is pretty much what the system does now, and it's been termed SATCAST, and I keep forgetting what that acronym is, even though I made it up. So anyways, you start out with the latest satellite imagery. Realistically, we started out with 3 satellite images at one time. So from GOES, we were doing 30-minute trends. The problem with 30-minute trends are that the cumulus clouds tend to evolve very quickly. In 30 minutes, we often can't track clouds very well. So now we use 2 images separated by 15 minutes apart. For MSG, you could use 3 images separated by 10 minutes apart. So 10 minutes, 5 minutes in the current. We pretty much monitor cumulus cloud development. This is really the niche. This is a really nice schematic that one of my collaborators made. Radar observations tend to get a lot of press in places that have radar. The niche for these convective initiation algorithm from satellite is the fact that you see the clouds before they make rain. So I said this many, many times already. We make the cloud mask. We produce what's called mesoscale atmospheric motion vectors. We produce motion vectors that have information on not just the geostrophic background flow, but also mesoscale flows. So some of the higher resolution, more deviant flows that occur around cumulus clouds. We track the cloud objects. We apply the Zinner et al. Approach where we look for object overlap. And as I just showed, we apply different spectral tests, whether it's 6 tests for attributes of growing clouds, And now we actually apply background information and do a statistical approach. And we get a map that looks like this. Kind of the blues are the no's and the reds are the yeses for which clouds are going to make rain in the next 1 hour. And so this is the approach. I've said this in words, but I'm just going to kind of talk this through with some schematics. So pretty much we identify our objects. So these are groups of pixels that are considered cumulus. We would apply them at time 1 and time 2. Ideally, we would look for object overlaps. So here's a case where we've successfully tracked 3 cumulus cloud objects, hoping they didn't evolve too much in that 15-minute time frame. Here's the cloud top cooling rate. This is a really simple schematic, but it's fairly effective. Pretty much if you have a cloud that gets colder with time, knowing that the lapse rate of the atmosphere is pretty much well described, you can actually say something, equate this to an updraft speed. So I have a question. So one of the criteria I use is a minus 4 degrees Celsius per 15-minute cooling rate. So does anybody have a sense for what kind of an updraft speed that is in a cloud? I don't expect you to do the math right now, but effectively, how fast do you think cumulus clouds cool off? If you have an updraft speed in a cloud of 10 meters per second or 20 meters per second, what do you think the actual cooling rate is? How fast do you think the top of that cloud gets cold? Well, what's really interesting, and I bring this up because it points to the limitations of the satellite observations. As shown this morning, you have this pixel that's roughly 3 or 4 kilometers as a square. There was a study done in 2003 that showed that if the cooling rate is minus 4 or minus 8 degrees in 15 minutes, that's a good sign for a strong updraft. That really equates to an updraft velocity of like 0.5 meters per second. So do you think that's appropriate for a cumulus cloud, 0.5 meters per second? Is that too high or too low? It's way too low. Way too low. So what's going on? So minus 8 degrees in 15 minutes from 1 IR pixel, that's a good indication of a growing cumulus. But the updraft speed, and you can do this on paper, comes out to be less than a meter per second. Yeah?
Yeah, I think it starts at quietening, so there's less of phase information.
Well, that's part of it. So remember I said that a cumulus cloud, you pointed out the scale is like 2 to 3 kilometers, and a pixel is like 3 to 4 kilometers. So initially, a cumulus cloud isn't filling a whole pixel. You're getting some of the ground temperature in there, okay? So that's one issue. So the other issue is the fact that, so you're getting a huge amount of averaging. I guess that is the main issue. You're getting a huge amount of averaging over this 3 to 4 kilometers, such that the real cooling rate in 15 minutes should obviously be something like 20 degrees. Whereas in reality, from satellite, especially with early growing cumulus clouds, might be only minus 4 to minus 8. So it's kind of an interesting thing. So we have to apply these tests that work very, very well, but in reality, they don't make good physical sense. And the reason is the limitations of our data. So this is another example of the 6.5 minus 10.7, or you could use the 6.2 minus 10.8 on MSG. This just gives a sense for the weighting function. This is the weighting function for the 6.5 channel, roughly the weighting function for the 10.7 or the 10.8 channel. When you actually do a channel difference between the two, what you end up with is something that's very, very large because the weighting functions are just from different altitudes in the atmosphere. So if these two 6.5 minus 10.7, if they have the same temperature, if they're very, very different in temperature, that implies that the cumulus cloud is actually very small. You have a cloud down low that's getting a temperature from here, whereas the 6.5 channel temperature is way up here. So if the cloud grows, what happens is that this channel difference becomes much, much smaller. So if it gets to be near 0, that implies that the cloud is way up here. So that's how we would actually use this information to diagnose physical properties of cumulus clouds. And that's actually, even though these are simple diagnostics to go through, they're actually really, really important when studying this phenomenon. And this, like I said, this is a kind of a general statement for anything you're doing is every data set has a limitation to what you're studying. So you got to be very, very careful to what you're using the data for. So as I mentioned before, and this is kind of my talk evolving into kind of where we were to where we're going. This is a yes-no forecast on how we would say, here's the cumulus clouds. We would apply these channel tests to them, or the interest field tests, and we would get a lot of these yes and no's. This is saying, yep, these clouds are going to make rain, but guess what? This one really close isn't. And what we found out is the weather forecasters, and this is where the scientists and us say, well, this is what you want. Here, take it or leave it, but you give it to the end users, and they actually give you feedback. So what we designed then was a probability, something that goes from a definite no to maybe a more positive yes, and you get something of a kind of a spectrum of probabilities per cloud. And what was really interesting in the United States, it's such a radar-centric world, when we put the satellite data into a color scheme that looked like weather radar, the forecasters liked it a whole lot better. So it was actually something where we'd say the colder colors here were really not likely to make rain, whereas these warmer colors were. This is an example over Colorado in the United States, pretty much how this works. We're focused on these areas. So you have this cluster of cumulus clouds here. We have some reds. This, now these are clouds where we've applied a lot of tests to them, plus some numerical weather prediction background information. And we find out that this cloud is definitely going to grow. And these orange clouds are probably in towering cumulus stage, but a little less likely to make rain. Now, if you just go forward in time for this particular case, this is pretty much how this looks from a forecast product. The one thing I do want to make note of, here's this cloud right here. Even though suddenly we go from we go from something of a red cloud, so this looks very, very promising, but the next image doesn't really show this, but the image after that shows this cloud wasn't even tested. So what is this? This is a cumulonimbus cloud. It's already making rain. So this product really gives us a sense for where it's going to rain in the next hour, and these clouds up here are really good examples too, where these are already cumulus clouds. And we're not going to apply any tests on these anymore because the weather radar is going to capture the rainfall signature. This is another example of how we would actually process these data. So here's our visible satellite imagery on the left. These are just clusters of cumulus clouds as identified by the forecaster. This is the older version, but nonetheless, these clouds were highlighted as very likely to make rain. And what's interesting is if you compare these patterns to this radar, which is roughly an hour older, we see very similar features. And so this is where our algorithm got some really good press in the sense that we actually are getting a sense for the forecaster is able to use this product in an absolute sense, pretty much. So you could almost say this cloud and this rain and this cloud and this rain, but also it's giving us a forecaster a good sense for situational awareness. What it is not highlighting are these clouds over here. This cloud, for example, did make some rain, but there's an awful lot of cumulus clouds in the scene that did not make rain. And so that's pretty much where our algorithm is having some impact. And what we did notice on this particular case is that this capping inversion feature here was the biggest reason we weren't seeing it rain everywhere. And we actually bring that information in. So going kind of the timeline of development of this method, these are some of the science papers that we've been a part of. I show this from the standpoint that, just this initial inception in 2001, we're actually down here now and we're actually implementing this procedure in a couple different real-time systems for the FAA. We're testing it in front of forecasters in the United States and in Europe. And getting some really good feedback. We're actually developing a lot more tools, and this is where the rest of my talk's going to go, is just how would you use cloud-derived parameters, numerical weather prediction model fields, and generate probabilistic forecasts that generally fit the end user quite a bit better than... So this is the product as it comes out every 15 minutes. We can produce we can produce forecasts over this entire scene within a matter of about 6 minutes. We have cumulus clouds that are already making rain, or cumulonimbus clouds here, but we also get a good sense for shallow cumulus clouds in this particular part of the world. Taller cumulus clouds here, the product produces convective nowcast or convective initiation nowcasts over the oceans as well, over mountainous regions. We're actually processing it for goes east and goes west, which is not a big leap, just the sense that it's actually being produced routinely over Europe by DWD as well. I don't know if it's all of Europe or just most of Europe, but and what this is this logistic regression probabilistic SATcast convective initiation nowcast, in which we take a lot more NWP fields. So one thing, when we kind of in the evolution of this product, we initially started out with just satellite data. And what we found out is that satellite observations, because we just use cumulus cloud information, it really was helpful to have background information from the instability in the environment. Is there a capping inversion in place? What we actually found out through some studies is that if we tried 50 different fields from a numerical weather prediction model and say 10 or 12 fields from satellite, and you put those all into an algorithm, you can actually get the importance. So you can actually figure out which of these 60 or 70 fields are providing the most information. And you can do this, there's statistical approaches that can do this better than the human can do this alone. So these are actually machine learning techniques. I would never have expected that this approach would have necessarily evolved into this, but when I first showed that schematic, I think it was my fourth or fifth slide, this is what happens with a lot of things, in the sense that you start out very, very simple, but then you can quickly go to more complex ways. Neural networks we've applied on this problem, random forest, which is a decision tree, logistic regression as another way of just grouping and understanding predictor fields. And just this is kind of a quick thing for what are the strengths and the weaknesses of these procedures. And if we looked at all these input fields, now this is just the partial list, but realistically we had a training database. In this case, it was about 9,000 cases from 2010 to 2011. We have these model-derived parameters that, again, the satellite doesn't really give us a good sense for, but the models do a very good job of providing these large-scale background fields. We take things like these channel differences from GOES. We do cloud types, the size of the object, land, sea, flag, things that the satellite can provide very, very well. We put them into these machine learning approaches. And we, like I said just a minute ago, we can provide an importance rank for which fields are highly relevant to convective initiation in the next 1 hour, whereas which fields don't have much value at all. I don't expect you to read all of this, but what it does show is there's a good mix of NWP and satellite observations that we do in fact use to make our nowcast right now. This is just this decision tree or random forest where you make many, many trees to try to find the best combination of variables. Again, this goes into things that the human being would not necessarily have guessed, but the random forest technique provides us a kind of an objective means of doing this. Again, this is another example where we can develop a feature selection map of which fields are more or less important. We can compare results. This is a receiver operating characteristic curve. This is neural networks, random forest, logistic regression. We find out that random forest or decision tree support. Decision tree methodology provides a much better, kind of the best skill out of all these approaches. And so we're actually developing this, and we have logistic regression, and we have this random forest procedure that's actually being produced. So this is some of the work that was actually done at MIT Lincoln Lab, one of our collaborators. So they took the satellite-based algorithm, they wanted to implement it in a Federal Aviation Administration system that produces convective forecasts for airlines. They have satellite environmental instability from models, other model-based fields. They do feature extraction, a little bit more sophisticated than what I did initially. They apply a machine learning approach, and they generate these nice probabilistic fields for convective storm initiation. This is something of a similar example where we have basically a 60-minute forecast of convective storm development from this. Yet this was the original without with the satellite only. So this is where the differences here are the fact that the model provides considerably more information than just the satellite fields alone. So anyways, so this method is good, but there's known limitations. And I think this is some of the limitations are the fact, this goes back to kind of the characteristics of the whole nowcasting problem, is one big limitation is the fact that the numerical weather prediction models often get the initial condition wrong. So even a background field we get from the numerical forecast isn't necessarily correct. The other is that the satellite presently is only available every 15 minutes. Another aspect is that we really can only detect convective storm development where we can see the cumulus clouds. So if we have an overlying higher cloud layer, that's not actually a very optimal situation, but we have a solution for this. So what we're really trying to do is limit the amount of false alarms. If you go ahead and say that every cumulus cloud is going to make rain within the next 1 hour, yeah, you're going to always be right, but you're going to probably be wrong like 98% of the time. And then at nighttime, we're limited to the fact that we don't have visible data, which is the highest resolution product we get from the satellite right now. So with this said, there's quite a lot of work that I'm still doing to try to get a better skill out of this procedure and desperately waiting on new satellite sensors. This is the cirrus cloud limitation. Effectively, if we have higher clouds here, we're never going to process our algorithm in this location. So even if we bring in numerical weather prediction model fields, there's nothing from the satellite. So we would basically say that there's going to be no chance of rain there. But as you know, that's certainly not the case. This is a study I did last year and was published this year, looking at if you bring in visible optical depths, you actually can do a really, really good job when if you have thin cirrus. So if the initial cirrus clouds have an optical depth of about 10 or less, you see enough of the cumulus cloud signal to make a nowcast. And so presently, without even knowing it, we were blanking out huge regions in our system that had thin cirrus that we could be processing. So this is where we would bring in a combination of information from retrieved properties as well as the raw satellite signatures. And this is kind of pretty much quantifying what I just said. Pretty much that if the optical depth is 10 or less, we get some really good signals from just changes in emissivity with growing clouds, ice water or cloud water paths increase. That we can take time rates of change of reflectance, emissivity, and optical depth, and we can actually get some really good signals for the growing cumulus clouds in that case. If the optical depth is 20 or more, so this would actually be a case like this where the optical depth was, I don't have a good example of that. Yeah, if the optical depth was on the order of this, there's actually enough information in that particular area using derived cloud properties to diagnose that a new cloud was going to develop in that area. So this is kind of an exciting finding that we're going to be implementing later this year. And so, so basically, again, I'm just repeating myself, we see rapid jumps in emissivity and cloud water paths as the cumulus clouds grow. We can use time rates of changes of these quantities to diagnose cumulus clouds, cumulus cloud development in areas of thick cirrus. So this is all pretty promising. One of the things that we've actually done, some of the more theoretical work, is if you can use the mean values of the interest fields, you can start to diagnose which areas of a given region are more or less unstable. And so a lot of times what you'll see in advance of thunderstorms developing is towering cumulus clouds. What you're doing here is you're trying to look for the outliers. So which clouds are developing more rapidly than their neighbors tends to be the ones that are more likely to make in new storms. And so this is a paper that's just about finished up now. So instead of treating the whole United States in the same, when you do a test of interest fields, instead of treating the whole United States as the same background or the same field, you would break your area up into these blocks. And just for reference, this is Florida, this is Wisconsin, this is Texas. So roughly 200 by 200 kilometer regions, you can start to subtract off the mean and look for the outliers. So anyway, so that's kind of, with the last 28 minutes I got here, I'm going to pretty much say where we started to go with this algorithm beyond just forecasting where it's raining. So the one thing is where there's going to be a first lightning strike, and then saying something about which storms are going to be locally intense. And these are actually really key features in the warning process in the United States, because you can get a lot of rain in the tropics, but it doesn't make a lot of lightning. I think most people around here would say that a storm, if you knew it was going to lightning a lot in the next 20 or 30 minutes, that would be a very valuable forecast. It would actually be very valuable if you knew the storm was going to turn into a supercell, or if supercells are likely on a given day, you could point and say that's where the first supercell is going to form. It gives a heads up to early severe weather occurrence. So these are some of the new areas. Some of the background on this lightning initiation indicator, the kind of lightning initiation nowcast, kind of the theory. This gets us into some new areas of cloud microphysics. Basically, I don't know how many are familiar with the non-inductive charging process, but this is very simply said that if you have a flux of water vapor through the, say, the minus 10 to minus 15 degrees C layer, what you start to generate is a lot of large ice particles like graupel. And if this flux continues, that's basically the charging region in the storm. So from satellite observations, we can detect an updraft, and we can detect if the cloud top is freezing. So you make the simple inference to say that where we have the strongest updrafts that are glaciating, we have a charging process that's very favorable for the occurrence of lightning. And so we take these tests that I showed earlier using the channel differences, and we've modified them and trained them on a training database to where it made lightning. And the people at MIT Lincoln Lab actually did some additional analysis, not only on the convective initiation part, but the lightning initiation part, using just cloud-to-ground lightning strike information, so where it first started to make lightning. Their goal then was to apply these tests. So we did a study back in 2009 and 2010 in which we said if the updraft strength was particularly strong, if the glaciation rate was very obvious associated with the strong updraft, and the cloud was tall, that's a good indication that it's going to start making lightning. So they took that information. We've actually developed something very, very similar for, this is a paper that just got published, for which lightning and non-lightning producing clouds in the MSG field of view. We see, again, a very strong delineation, so there's absolutely no reason we couldn't apply these approaches over Europe. And this is, again, that same table, but this is for cloud-to-ground lightning, storms that produce cloud-to-ground lightning versus those that did not. So pretty much lightning events, the cloud would look like this with a very thick anvil, a lot of ice in the anvil, whereas non-lightning events would probably look like this with very shallow looking cumulus clouds, not a lot of obvious glaciation or very weak updrafts. So, and so the MIT Lincoln Lab people, like I said, they took the same approach with convective initiation as they did with lightning, applied machine learning approaches on a combination of model data and satellite observations. They went ahead and used, as I said, they used model information from a variety of sources, other predictors of thunderstorms. They used these indicators from satellite, environmental information from a model. They developed these field importance approaches, which fields are more important than others when developing lightning forecast, developed a similar receiver operating or a ROC curve for neural networks, random forest, and logistic regression. And they were actually able to forecast then, kind of produce this 1 hour probability of lightning. Very similar to what a convective initiation field would look like, but actually only over a subset of those clouds that are likely to make lightning in the next 1 hour. And what's really nice is that our lead time for rainfall arguably is about 20 to 30 minutes. If it's really, really unstable, maybe like 15 minutes. If it's weakly unstable, maybe up to an hour. But for lightning, we get lead times at least 15 minutes longer, because usually it rains for a while before it makes lightning. So this is actually some really good news. Here's our 1 hour lightning probability or lightning initiation probability forecast. You can actually change this to 20 by 20 kilometer regions, which actually for airports is a really valuable. The 16 kilometer rule tends to be a 16 mile rule, or 20 kilometers tends to be a really nice scale for when does a airport get concerned about people on the ground getting struck by lightning. So another approach, and I think I'm going to finish a bit early because number one, it's really warm in here, and number two, I'm kind of getting out of slides. So maybe if you can stay awake for 10 more minutes. The next thing I'm having a grad student do, and I think he really doesn't like me, is so not only could we say which storms are going to make lightning, but there's a product that came out from the weather research and forecast model from a guy in our building. They actually developed a product that uses model fields on, now this is model forecasted convection, so we know it's not going to be right. But what it can do is help us develop a physical understanding between the flux of ice through this minus 15 degree layer and how much lightning occurs. So I'm having the student develop a relationship between the satellite-based lightning initiation forecast, so these yes-nos, yes it's going to lightning, no it's not, and this product. So the question would be is, yes it's going to lightning, and it's going to lightning this much. We're going to have a flash density of 6 or 8 or 20. For people not familiar with lightning, a flash density of 20 is very, very frequent lightning. A flash density of 6 is frequent, but not that frequent. So anyways, that's kind of a forecast, something looking forward to the future is lightning warnings. And so this is actually combining a derived product from a model with satellite information. And that's something I think he'll be done with next spring. This is just kind of a schematic for how he's doing this. This is the SatCast 0 to 1 hour Nowcast. Here's where we're going to say it's going to make lightning. His job is to give us a sense for how much lightning is going to be produced if you use the model field to give you that information. This is just some of the distance weighting he's going through. The more I stress him out, the more complicated this figure gets. So with that said, I only have two things that I'm going to finish off with here. One is the storm intensity and how could we estimate from satellite and other information how strong the storm is going to be, as well as new techniques and directions. So in terms of the whole premise for warning in the United States, and this happens, I just pulled this is a mesocyclone. The tornado signature is actually right there. And you can see this warning that looks like this. So this is very typical of what you see in the United States. The warning, the box that states within the warning is often not a square. It's often a cone, is what they call it. And to some extent, it gives this uncertainty of the whole forecast. One would assume the tornado is going to move like this, but it's not necessarily going to move in a straight line. Well, what some of the research we're doing in terms of storm intensity would be to go way back here and say, if I can produce a convective initiation nowcast on what's to become a supercell, then apply tests to say, well, how strong that storm is going to be. The forecaster is starting to look at this storm way back here in time versus maybe here when it first starts to make a hook echo. So this is kind of where this work fits into the warning process. This was for the Moore tornado, not the one that this is the first tornado that occurred in that week, the first F5, not the second one. But what we did see is that you're getting this first lead time on some of these cumulus clouds way in the west. So this is way west of Moore, Oklahoma. Here's this first lead time on this storm. So we had a convective initiation forecast 45 minutes in advance for this one cell. And then there was a second cell that developed in which we produced about a 15-minute lead time because it was quite unstable. But nonetheless, this is the cell that eventually went on to produce the tornado. So the tornado occurred just before 3 p.m. local, or 1956, and so, you know, roughly an hour lead time on on this supercell from this. Now, radar helps as well, but this gives us this added lead time. So the convective initiation product provided a 15 to 45-minute advance notice to convective cloud development in an environment prone to producing supercells. So, so that again is kind of the niche for this work. This is just kind of how the day evolved. Turns out that I think this was the main supercell that produced that tornado out of everything. So anyways, this is a busy slide, but I really wanted to just say a couple things. There's a lot of proven methodologies on storm nowcasting and diagnosis that I've done. We can bring in a lot of work from Danny Rosenfeld, for example, who've used cloud-derived properties associated with severe convection to locate things like what's the glaciation temperatures and how small the particles are at cloud top for severe convective storms. So basically what we want to do is develop about a database of many attributes. Again, we're not just going to look at the ones we think are going to work, but maybe look at a whole lot more and apply some sophisticated algorithms to help us figure this problem out. So basically we want to form a new version of this SATcast that exploits visible and infrared data that nowcast intense storms for up to an hour before they occur, and then eventually provide this to an operational forecast group just for an evaluation. So here's the timeline, convective initiation down here. We're going to monitor the storms in this first 45-minute time frame, or monitor the cloud growth, maybe as short as the first 10 minutes. So maybe in the first 5 or 10 or 15 minutes of this cloud's development. And then we're going to start to say, well, what's going to happen out here? These are really, really new results, and this is just kind of schematically what severe storms look. We end up with really rapid storm growth for the intense storms. Might actually have a wall cloud by the time it's over with a strong overshooting top. Whereas the weak storms grow, they'll be very narrow. They may actually begin to dissipate by that 2-hour time frame. So we should, from satellite, get enough indication which storms, even in a severe weather environment, are going to be good. And these next set of slides are pretty much how you would diagnose this. This is the microphysical properties that you would start to see at cloud top and within the cloud for like a weak updraft, kind of an increasing updraft strength, maritime strong updraft, and what you find is that the precipitation process tends to begin higher in the cloud in terms of ice microphysics versus warm rain. You bring in aerosols and it even gets a little bit more dramatic. So basically what we find, and I'm going to go through the next few slides kind of quick, for weak storms, we might have strong initial growth, but the cloud top glaciates at a at a relatively warm temperature with large particles. That's simply because the particles in a strong updraft don't have time to grow compared to those in a weak updraft. In a moderate storm, we would have cold glaciation temperatures, so relatively large, slightly larger or slightly smaller effective radii, but I think this is a little bit wrong here, but for the most part what we would find is our glaciation temperatures would be, say, minus 30 Celsius, but in strong storms we would have strong initial relative growth, cold glaciation temperatures maybe down to minus 35 Celsius, and this particular storm went on to produce a waterspout over the Mediterranean that impacted an island. But anyways, we would get, so kind of some of the initial results of this, again, kind of schematically, we can evaluate the intensity in this first 0 to 30 minutes. And this is a really important thing. What I'm finding is that if we have 2.5 minute or 1 minute data, you can actually make the diagnosis of really, really strong updrafts using those time differences very accurately. And so this is some of the new work that we're going down the road to do. And so some of the early work, this is something that I just finished last week. We find out in that first 5 to 15 minutes, things like the cloud top temperature, the 5-minute temperature trends, and the glaciation temperature give really strong indicators to which storms are going to become intense. But by 20 to 30 minutes, feature expansion rates, glaciation temperature, and effective radii start to give a lot of information. Whereas later on, even though you can't read this 15 minutes, it's a 6.2 minus 7.3 channel difference, gives an indication of overshooting tops. So this is a really nice view of how do you use satellite observations with physical principles to predict convective intensity. So basically for intense storms, early signatures are strong updrafts and relatively low temperatures when the clouds first glaciate, whereas later indicators are more rapid cloud feature expansion, relatively small effective radii, and after 30 minutes, the small, basically small 6.2 minus 7.3 channel differences suggest the presence of an overshooting top in a really cold anvil. So all I want to say on this last slide here, there's a few slides left, pretty much what we're challenged to do, let's face it, if I don't do this, and if I don't go this route, I'm probably not going to get any more funding for the rest of my life, unless I start selling things on the street. So, and I hope this isn't recorded. So, no. But anyway, so the goal here is that satellite observations are great. Satellite plus NWP is better, but we really want to start bringing in other data sets like lightning and radar observations to try to get a better sense for how these data sets relate to one another. And frankly, the world is going to this 1-minute data. I mean, if you look at phased array radars, that's actually less than 1 minute. I think you can get those observations from. Satellites going to 1-minute observations. I think GOES-R is going to have 30-second observation capabilities. Lightning observations, these networks, these lightning array networks are producing observations extremely frequently. So I think in time, the nowcasting world is going to get flooded with huge amounts of information on very short-term changes, which really bodes well to predicting, again, storm intensity and which storms are going to make lightning or which storms are going to make heavy rain. This is just a recent study on how satellite observations behave for satellite and radar together for lightning and non-lightning storms. These are some CFADs or contoured frequency something diagrams from dual pole observations. So this is basically what the radar would look like as a volume averaged over time, kind of like a histogram with altitude. And you're getting a really nice glaciation ice graupel signature in the mixed phase. What we actually been able to do is quantify the ice volumes. You see at cloud top that when you get a switch over in some of these glaciation indicators from satellite, we can actually quantify how much ice is probably present to an order of magnitude at the cloud top from radar, which is really, really neat. And we've actually looked at these other dual pole variables in that talk that I saw on Wednesday. Really did a very good job of interrelating lightning and dual pole observations with, and I'm going to say more on that this afternoon when I talk about overshooting tops or later today. Just a couple more slides. This is actually a new project that just started in which the people at NCAR are taking our observations and assimilating them into models. So if you use the satellite-only data and you, as I said right at the beginning of the talk, the biggest problem with weather forecast models is they tend to start out with this initial condition, but it takes them 4 to 6 hours to develop a forecast that probably is not going to get the rain in the right place at the right time. So if we can assimilate the satellite observations that look like this on the model grid, we can actually say something about that after 1 hour with the satellite, this is what the convection looks like in the model versus without. So we're getting a better sense. The satellite's helping to produce the storms in the right place at the right time in the model. And that's actually a really, really interesting finding. Even more interesting is that after 2 hours and 3 hours, this information stays in the model. So it does give a sense that the model wants to make storms. The satellite's actually producing the storms at the right place at the right time. second to the last slide here, this is the 1-minute observations from GOES. I thank Chris Bedka for the satellite loop, but this is really where his focus area is this overshooting top, but there's an awful lot of information right in here that's going to give, what's going on here that's we can use for convective storm initiation forecasts, as well as along the lines of what I talked about. This is kind of a vision for the future. I've said a lot of this already. So a big thing really is 1 to 2.5 minute data from some of these sensors. Really getting a sense for kind of pushing this to the next level. And I just want to say thank you very much, and thanks for staying awake after lunch. And we'll talk to you in about 37 minutes. So.